We'll just wait for a few more minutes to see if everyone joins in and then we'll begin. Let's begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So we'll go over the questions of the week 1 and week 2 assignments. Hopefully you've all done them. So let's begin. Okay. The first question was, a student writes the drag polar equation in the form CD equals A plus BC. Then A, B, and C are respectively what all? Given that aspect ratio is AR, E is the Ostwald's efficiency. So which one do you think is the right answer? You've all done the assignments, right? It's a very straightforward question. Which one do you think is the right answer? What is the typical drag polar equation? CD equal to? What is the drag polar equation? Option C. Okay, so let's just write on the drag polar equation. Can someone else tell me what is the drag polar equation? It's one of the first equations we discussed. CD equal to? None of you know the answers except, yeah, Shreyas. CD naught plus KCL square. Yes? Do you remember what each term was? What was CD naught and what was KCL square? What is this and what is this? What was CD naught and what was KCL square? What types of drags? We had discussed this also, right? What was CD naught and what was KCL square? How are they different? What are their names? Yeah, but there are two types of drags, right? Zero lift drag is CD naught, yes, but what is it referred to as? It had names. We had discussed this. Two types of drags. Yes, the drag due to lift is referred to as what? You remember something known as induced drag? Wait a minute. This is induced drag. And what was CD naught? What was that called? Do you remember induced drag? Am I audible? Okay, so you remember induced drag. What was the other one? CD naught. What was it referred to as? Parasite drag. Exactly. This is the parasitic drag. Okay. So now CD, the drag polar, CD is equal to CD naught plus KCL square. CD naught is the parasitic drag and K is equal to 1 by pi EAR. So in the equation that is given, A would be CD naught from this equation. Just equate what we wrote and what is given in the question. And B would be K, which is nothing but 1 by pi EAR. And C would be CL square, right? So yes, option 3 is right. Two of you had answered. Option 3 is right. Okay, let's go to the next question. So this is the formula that we use, CD equal to CD naught plus KC square. That's the drag polar, where CD naught is the parasite drag, KCL square is the induced drag. Why is this induced drag coming into play? We had discussed this extensively, I think, last week. Why do we have induced drag? When there is a lift generated, why do we have an induced drag? Due to wingtip vortices. Yes, there is a wingtip vortice. It occurs because the flow above and below the wing meet at the wingtip, and then it becomes an unsteady flow, and then you have vortices generated. which travel backwards, and the downwash also creates a problem. Okay, so that's why there is a drag due to the lift generated because of the uneven nature of the forces above and below the wing that meet at the tip. Okay. Next question, calculate how much power will be required to maintain cruise speed of 83 meters per second if thrust required is 976 Newton. So this is a straightforward question. They've given you thrust, they've given you velocity, they've asked you to find out power. What is the equation for power? Power required, power equal to? Power equal to TV, correct. Thrust required into velocity. Thrust required is 976, velocity is 83. Multiply this and you will get 81, right? So that is this one. Correct? Yes. Now, I think we discussed this question even before the assignment, something similar. If the center of gravity coincides with the neutral point, then the static margin is, what is static margin? I don't know Hindi. I don't think I can do that. I'm really sorry, Satvik, but I don't speak Hindi. Okay, so if the center of gravity coincides with the neutral point, what will the static margin be? So what is static margin? What is static margin? Distance between CP and CG. Okay, so there are several such points. Let's just discuss all of them. CP is one, CG is one, neutral point, then you have aerodynamic center. Any other such points of reference? None. Okay, so CG we all know, right? CG is known. The center of gravity where the mass acts, where the weight acts. Okay, the point at which, through which the weight acts. Okay, CG. What is CP? CG is center of gravity. What is CP? Center of pressure. Yes. What is center of pressure? Can you define it? We had discussed this again, I think, first 2 weeks. Or if you've done the aircraft performance course, this is, or aerodynamics or anything, how would you define center of pressure for an airfoil or center of pressure? Where the total force acts, where, yes, so where the aerodynamic forces lift and drag act, okay? So that is center of pressure. What is neutral point? Okay, let's go first for AC. What is AC? Aerodynamic center. What is aerodynamic center? What is aerodynamic center? Where the moment is independent of angle of attack. Exactly, where the pitching moment is independent of angle of attack. Okay, that's the aerodynamic center. So where Cm or pitching moment coefficient is not dependent on angle of attack. Okay. What is neutral point? We are discussing neutral point. Now, what is neutral point? We had to come up with AC. We could not do our analysis about center of pressure, even though that is where the forces act, because the center of pressure keeps changing with angle of attack. So across the flight, when the angle of attack keeps changing, the center of pressure would keep changing, and we cannot do our analysis about a point that keeps changing. So we coined the aerodynamic center, which is the point about which pitching moment is independent of angle of attack, and you can perform all your analysis without any difficulty. Okay. So that's why we came up with aerodynamic center. What is neutral point? What is neutral point? where Cm alpha is equal. How is it different from aerodynamic center then? Both are the same, right? I think this would move a lot faster if you just unmuted yourself and answered, if that's convenient, because typing might take time. Yeah, so you were told that aerodynamic center is the point about which moment is independent of angle of attack. And now when I asked for neutral point, you said Cm alpha is 0. Isn't that the same thing?
Yeah, it means, I mean, del CM by del alpha.
Del Cm by del alpha is Cm alpha, right?
Oh, okay. Sorry. My bad.
Cm alpha is the slope. So if the slope is 0, it means that the pitching moment remains constant throughout the flight duration, right? So it's the same definition. So how is neutral point different from aerodynamic center then? Anybody else try? His answer is right, by the way. So neutral point is the point where Cm alpha is 0, is the point where moment is independent of angle of attack. But then how is it different from aerodynamic center?
Uh, I think it is the where the restoring moment is not generated. Is that point? If we give a disturbance, then restoring moment is not generated. It will remain at its position.
That is same for aerodynamic center. So the difference is that aerodynamic center is for just for one wing cross section, just for an airfoil, just for the wing. Neutral point is the aerodynamic center of the entire flight. So it is basically the same point, but for a wing alone, it's called aerodynamic center or any such structure. So if I just say tail, it will be the aerodynamic center of the tail or aerodynamic center of the wing. The aerodynamic center of the entire flight is neutral point. Okay, that is the only difference. Otherwise, neutral point, aerodynamic center, definition-wise, properties-wise, it's the same thing. Okay, so now tell me what is a static margin. What is static margin? Difference between. So somebody had earlier said that it's the difference between CP and CG. I'm not sure. Something, yeah. So distance between CP and CG is what somebody had said. Now can you tell me what? It's not the distance between CP and CG. That's not the right answer, but it's along similar lines. Distance between. Just a minute. Yeah. So distance between static margin is
Neutral point and CG.
exactly. So it's with distance between neutral point and CG. So if your center of gravity coincides with neutral point, static margin will be 0, right? Because there is no distance between CG and neutral point. Static margin will be 0. So that is the right answer. So this is just the equation. So static margin is the negative of the slope between Cm and Cl, okay? Or the negative of the slope between Cm and alpha. So it's defined as the distance between neutral point and CG, not CP and CG. It's neutral point and CG, okay? So in this case, the answer would be equal to 0 because both CG and neutral point are the same point. There's no distance between those two, okay? Now, because of the positive camber in the airfoil, what happens? Does CL max increase, alpha stall decrease? Which of those? So just compare a symmetric airfoil and a positively cambered airfoil, and then you'll get the answer. The lift slopes, lift curves of both of these. So for a symmetric airfoil, it's something like this, where CL versus alpha, where this is CL max and this is alpha stall. So this point is alpha stall 1 and this is CL max 1. Now for a cambered airfoil, what happens? You slide up the line, right? Across the plane, you just slide up. That's a typical variation for a positive camber. So it'll be something like this. Now what happens? So this was for symmetric and this was for positive camber. Yeah. So will the CL max increase? What will CL max be? CL max 2 is greater or less than CL max 1? So CL max 2 is this, right? This point. So CL max 2 is greater than CL max 1, correct? What about alpha? Alpha stall. It will be lesser, right? So this is alpha stall 2. So alpha stall 2 is less than alpha stall 1, correct? So that first option is the right option. Okay, let's go on to the next one. Okay. At any point, if anybody doesn't follow, just stop me, okay? We can discuss it again. Okay. With the increase in altitude, the air density dash and the stall velocity dash. So does the air density increase or decrease? So as height increases, what happens to density and what happens to V stall? As height increases, density decreases, right? What happens to V stall? What was the formula for V stall? So again, one of the first few formulae, only few formulae in fact that we've studied. What was the formula for V stall? Under root
Under 2 W by S by rho CL.
rho CL max. Okay, so now what happens? From this equation, you can directly see that when the altitude increases, density decreases, and so the V stall
Increases.
increases. Exactly. So density decreases and V stall increases. That is the right option. Okay. Yeah, so this was the formula for V stall, which you have rightly said. Let's go to the next question. Okay. The wing loading for an aircraft is 45 kg per meter square and CL max is 2.3. The Vstall, find the Vstall of the aircraft given the density. Direct formula substitution, we just saw the formula. Vstall is under root 2W by S rho CL max. So direct substitution, just do that. 2 into 45 by 1.225 into 2.3. What is the answer? Oh, that will be a 9.81. So something around 17.7. Yeah, so that is the right answer. Okay, let's go to the next question. Yeah, so this was the formula that we used, same as the previous question. Okay, find CL by CD max if drag polar of an aircraft is given by. So what was CL at CL by CD max? We had studied a table, remember? So what was the CL?
CD naught by K.
Under root CD naught by K, right? CD naught by K. And what was the CD? CL by CD max. So you can
2
just,
CD naught.
yes, 2 CD naught. So just find out the ratio. So it will be CL by CD max would be under root CD naught by K by 2 CD naught. So what would it be? 1 by 2 under root 1 by K CD naught. Now just substitute the values. 1 by 2 under root 1 by K here is 0.075 and CD naught is 0.05. What would the value be? Something around 8.165. Right, so that is this. That is the right answer, correct. Yeah, so these are the formula that we used. Now we'll move on to week 2 questions. Again, a very easy question to begin with. The aerodynamic forces acting on the aircraft depends
Explain
on.
me one more time. Last problem.
Sorry? Did somebody say
Once
something?
again, explain.
I can't hear you. Can you speak a little louder?
Can you please explain me last problem one more time?
I'm sorry, it's not audible at all.
Can can you please explain me last problem one more time?
This one? Is this the question?
Yes.
Okay, yeah. So I'll
Yes.
just, yeah, so here. So we had seen that the CL for the case when CL by CD is maximum, CL by CD is maximum is given by under root K by CD naught. CD naught by K, sorry. Just so it's CD naught by K. Similarly, so if we just plug in this value, so CD equals CD naught plus K CL square, and CL is given from here. So you write CD naught plus K CL square would be CD naught by K, which is 2 CD naught. Now they've asked you to find the ratio CL by CD max. So just take the ratio of these two. So CL by CD max would be this quantity upon this quantity. So it would be under root CD naught by K by 2 CD naught. So if you simplify this, you get 1 by 2 square root. If you take it inside the square root, you get CD naught by K CD naught square. And then you get 1 by 2, 1 by K CD naught. And this is CD naught. And this is K. Correct? Just substitute the values and you will get it. Is this okay? Okay. So let's move on to week 2 questions. So aerodynamic forces acting on the aircraft depends on relative ground speed, wind speed, relative airspeed, or none of these. So when the aircraft is flying in air, it encounters a velocity V infinity we call it. Yeah, we usually denote it by V infinity. This V infinity is what produces the aerodynamic forces, lift and drag, right? So what is this V infinity? Your lift is what? Half rho V infinity square SCL. Option C, relative airspeed. Yeah, why do we call it relative airspeed? Can you give me some example where the object is stationary and here the object is moving in the air, right? So you can give me some examples where the object is stationary and then it meets an oncoming flow. Wind tunnel, perfect. Yes, wind tunnel. So that's how we do our measurements in the wind tunnel. We thrust equal to drag ratio. I'm not sure, Satvik, what you mean by thrust equal to drag ratio. Okay, so what Prajwala said is right, wind tunnel. So that's where the object is stationary and it meets an oncoming velocity. So if you supply it with the same relative airspeed, it will simulate the conditions in actual flight. That's how you calculate your measurements. Okay, so yeah, this is relative airspeed. Correct. There. For an aircraft to be statically stable, the value of dCm upon d alpha should be, this is nothing but Cm alpha. Okay. So this is Cm alpha should be positive, negative, 0, none of these. Negative, correct. So your pitching moment versus alpha curve is Cm versus alpha. It's something like this, right? So if your aircraft is subject to a positive gust, so it has a positive change in angle of attack. If your aircraft is stable, it will tend to come back. So it will produce a nose down moment. So for positive delta alpha, you need negative Cm or pitch down. right? Negative Cm is pitch down, which is why your dCm upon d alpha should be negative. So positive delta alpha should have a restoring or negative Cm pitching moment, okay? That's when the aircraft is called statically stable, longitudinally statically stable. Okay. Now, an aircraft is equipped with symmetrical airfoil. With a complete aircraft, the lift curve slope is 0.085 degree. Alpha max or the stall angle is 15 degrees. What is the stall velocity if the wing loading is 41 kg per meter square? Acceleration due to gravity is 9.81 meter per second square and density of air is 1.225 kg per meter cube. How do we do this? They've asked you to find out stall velocity. Again, put up the formula that we've used. That is under root 2W by S rho CL max. Now, wing loading is given in the question. Where is the wing loading? Yeah, this is the wing loading. Density is given. What we need is CL max. How do we find out CL max? They've given you the stall angle of attack. What can you get from that? So at the stall, you have CL max, right? You remember the graph? This is the lift curve, CL versus alpha. This is your alpha stall. And this is your CL max, correct? So if alpha stall and the lift curve slope are given to you, how do you find out CL max?
CL alpha into alpha.
Correct. So it's just CL alpha into alpha max. Here it is 0.085 per degree. And this is given in 15. So how much would this be? 1.275. Plug that in here. So it will be 2 into 41 into 9.81. 1.225 and CL max is 1.275. And this would give you somewhere around 22.69 second. So this is the answer. Okay. Move on to the next question. Yeah, so this is the formula that we use that we've been using for 2-3 questions now. Okay. For a propeller driven aircraft, the range is maximum when? So propeller driven aircraft was the first condition that we saw. So what was it? Minimum thrust required, right? Or minimum drag or minimum thrust required. Correct? So it is. So it is TR minimum. So what was the value for CL and CL by CD? What was the condition on CL by CD? What was the value of CL? Maximum range. We just used this formula now in one of the previous questions. Maximum range of a propeller driven aircraft. You remember this table? So from this table, can you try to tell me? Given directly there, right? So which option would it be? Is it option D? Maximum range. So it's this condition, right? So CL by CD is maximum and CL equals under root CD naught by K, which is the first option. Correct? It's the first option. That's the right answer. Now, the next question is very similar, but it says what is the maximum endurance condition for the same propeller driven aircraft? So here it's minimum power required, right? What is the answer now? D. Yes. Now here D is the right answer. So it's the maximum endurance, so minimum power required case here. So CL 3 by 2, CL raised 3 by 2 by CD is maximum. And CL is under root of 3 CD naught by K. Okay. Okay. Now, this is very similar to one of the questions that we had done in the previous sessions. So, power required curve for a propeller-driven airplane is shown in the following figure. What are the velocities corresponding to maximum range and maximum endurance respectively? So, we just saw that the maximum power, maximum endurance corresponds to PR minimum. Correct? So what would the velocity be for maximum endurance? Maximum endurance, which will the velocity be? VA, VB, VC, or VD? For maximum endurance, yes, VB. But that is this point where the power required curve reaches a minimum. So that is VB. Now, for maximum range, max range, you have thrust required to be minimum, right? We had done the same thing in the previous class. So which one would it be? So you remember this graph that we had discussed in the last class. So minimum power required is this point. That is the point where you have maximum endurance, right? So for maximum range, you need minimum thrust required. That is the point where the line joining the origin and any point on the graph gives you the minimum slope. So this is the equation that they have done to follow it. So you just keep drawing straight lines from the origin to any point on the graph. And where it becomes minimum, right? So when this theta is minimum, it gives you the velocity. This point gives you the velocity. So here it would be VC. Yes, you are right. So VC. So the option would be VC VB, right? They've asked you range first and then endurance. So VC VB. So that second option is the right option. Okay. Now, in the following figure, the area under the curve represents. So on the y-axis, you have V infinity by Cp. On the x-axis, you have the weights. So direct formula. So what was the formula for range? The direct formula substitution. You remember the range and endurance formula? What was the formula for range? Integral W1 to W0, 1 to the initial thing. What was inside the integral? That was V infinity by Cp dW. What was endurance? U1 to W0. What was inside the integral for endurance? So this one is range, right? So it's range. So for endurance, what was the formula inside the integral?
1 by Cp.
1 by Cp, exactly. So it's 1 by Cp dW. In this case, it's the correct answer is range. Next question, in fact, asks you about this one. So here in the y-axis, you have 1 by Cp. X-axis is same, it's the weight. So here, it would give you endurance. Endurance is integral W1 W0 1 by Cp dW. Okay, so here it gives you endurance. Okay. Okay, now let's discuss some of the contents that week 3 covered. So before that, we'll just study the basic terminologies of airfoil. So all of you probably already know all these things. So each airfoil has a leading edge and a trailing edge. And so how is the chord line defined? The chord line shown in orange here, how is it defined?
Line joining the leading edge and trailing edge.
Correct. Straight line joining the leading edge and the trailing edge. What is the maximum camber line? This I think we discussed in the last class. What is the maximum camber line?
Line dividing airfoil to equal halves symmetrically.
Okay, the line that is equidistant from the upper surface and the lower surface. Yes. So what is the distance between this mean camber line and chord line? What is it called? The maximum distance between the mean camber line and the chord line. What is it called? You can look at the figure and yes, it's called maximum camber. It's this one in blue, written in blue. So and the maximum thickness is the maximum distance between the upper surface and the lower surface. These 2 points, the location of maximum thickness and maximum camber, may or may not be the same. Okay, it need not be the same. In this case, it's not the same. So it can be different points. Then what else is given here that we have not discussed? Yeah, leading edge radius. So the leading edge is in the form of the arc of a circle. So the radius of that is another geometric parameter that is used to define airfoils. Okay. So next, yeah. So this is a slide from last class. So some of the parameters that we use to categorize airfoil or pick an airfoil for our design. So we want, what characteristics do we want? So these are the aerodynamic aspects. Aerodynamic, and these are geometric. Like upon changing the geometric aspects, these aerodynamic parameters change. Okay. So we want our CL alpha to be as high as possible. We want it to increase. Why? So if you have two airfoils, one like this and one like this, CL versus alpha, at the same alpha, the second, so if this is the first and this is second, the second airfoil gives you more lift. Okay, so we want CL alpha to be higher. That's one design consideration. Then what do we want? We want to delay our stalling angle as far as possible so that you can operate or you can fly for a longer range of alphas. Okay, so you can operate for a larger period. So you want your alpha to be as delayed as possible, alpha stall. Okay, then you have CL max. We want CL max to be as high as possible. Similarly, like similar to the first case. So for the same angle of attack, you need to get a higher CL. That's why you want your CL max to be as high as possible. Then you want your critical Mach number to be as high as. What was critical Mach number? We had discussed this in last class. What was critical Mach number? M critical Mach number.
Which is 1.
I'm sorry, I couldn't hear you.
Where local Mach number reaches 1.
Correct. The Mach number at which any point on the airfoil, the flow reaches Mach 1. Okay, that's critical Mach number. We want it to be as high as possible because we want to delay the occurrence of the sonic flow as much as possible. Okay, because when you have sonic flow, you attain sonic or supersonic flow, it highly disturbs the flow over the airfoil and does not give you the required characteristics. Okay, so one of the parameters that Sir had considered for delaying critical Mach number was thickness to chord ratio, right? Thickness to chord ratio. How did it vary? So if this was M critical and this was thickness to chord, this was the variation. Okay, something like that. So it's decreasing with increase in critical with increase in thickness. Similarly, something else that depend on thickness to chord ratio was CL max. So CL and thickness to chord varied something like this, and around 14 to 15% is when you got the highest CL. Okay, so this is another geometric parameter versus, or the other way, aerodynamic parameter versus some geometric parameter. Something else is, so one of the geometric parameters here, we have nose radius, thickness to chord ratio. Can you name some other geometric parameters related to airfoil that could change your aerodynamic properties? Two other things Sir had discussed. One is camber. We had discussed this in the last class. And the first question also was this, right? So if you increase camber, what changes? So your CL max changes, alpha stall decreases, CL max increases. So camber directly relates to CL max. Correct? What else? some other property, some other geometric property. Sir had discussed this in the class. So aspect ratio, right? Aspect ratio, AR, not A upon R, AR. What it affects in the variation of CL versus alpha. So one graph is like this. This is like this. So this is for a lower aspect ratio, say higher aspect ratio, say 5. And this is for aspect ratio 1. So as the aspect ratio decreases, your slope reduces, your alpha stall gets delayed. Okay. So a combination of all of these parameters helps you pick your desired airfoil. Okay, so it's like a trade-off between different parameters. It's an optimization depending on your requirements. Okay, another thing that we had missed here, CMAC should be positive, this point. Why should CMAC be positive? Why should CMAC be positive? We had discussed this, right? CMAC is nothing but CM naught. Why should it be positive?
To have a positive trimming angle.
Yes, to trim the aircraft at a positive angle of attack, correct. How do we get, so for a symmetric airfoil, CMAC is 0, right? For a positively cambered airfoil, the CMAC is negative. And how do we get a positive CMAC?
Reflex airfoils.
Reflex airfoil, exactly. So you get reflex airfoil. Reflex airfoil is nothing but a positively cambered airfoil that has a slight upward curve towards the trailing edge. Okay, so what it does is it moves the CP ahead or brings it to the AC. So then you have a positive CM. Okay, let's go to the next slide. Yeah, so this is just discussing what the critical Mach number is. So if your flow is below the critical Mach number, which is 0.72 in this case, it's a smooth laminar, almost laminar flow throughout the airfoil. When it reaches the critical Mach number, so the leading edge may encounter a critical Mach number, that is Mach of 0.72. But about this point on the aircraft, you have Mach equal to 1 on the airfoil. So the Mach number at which any point on the airfoil encounters a sonic flow, encounters Mach 1, is called critical Mach number. Now what happens when you fly beyond this critical Mach number is that it produces a normal shock wave on the upper surface. Now the flow after this normal shock wave, it may or may not have a flow separation. There is a possibility for a flow separation. Okay, so it's probably just the intermediate between laminar and turbulent flow, and it's maybe going to start separating. Okay, so these are undesirable characteristics. We do not want this. So we want to delay this. We want to have as high as a Mach critical number as possible, right? So that is one criteria. I think somewhere I will have something. Okay. Now let's just discuss the various NACA series, NACA 4, 5, 6 series, what each digit means. We'll just go over and we'll discuss this with examples so that it's easy to understand. Okay. So the NACA 4-digit airfoil series, in that the first digit represents the value of maximum camber in 1/100th of C. Okay, so in this case, what would it be? The first digit. So it will be 2/100 C. That will be 0.02 C. So maximum camber of this example is 0.02 C, right? Then the second digit gives you the location of this maximum camber in 1/10th of C. So what would it be here? For this example, what would it be?
0.4 C.
Exactly. So it will be 4/10C, that is 0.4 C. And the third and the fourth digits gives you the maximum thickness in 1/100th of C. So here it will be 12 by 100 C, which is nothing but 0.12 C, correct? So this is how we characterize or name the airfoils according to the NACA series. This is the NACA nomenclature. So this is the 4 series example. Now let's go to, so this is just the values that we have computed. I've just written the values. Now let's go to the 5 series. So this is the example for the 5 series case. Now in the 5 series, the first digit when multiplied by 1.5 gives you the design lift coefficient in 1/10. So what would the value be here?
Point 3.
0.3. So it's nothing but 2 into 1.5 by 10. So that is 0.3. What is this design lift coefficient? Also CL naught, right? So the lift that the airfoil is designed to produce. Okay. So that is what it is. Okay. Second and third digits when divided by 2 gives you the location of maximum camber in 1/100th of C. So what would it be in this case?
Point 15 C.
So it will be 30 by 2 into 1/100 C. So it will be 0.15 C. Fourth and fifth digits, just like the 4 series case, would give you maximum thickness in 1/100th C. So again, it will be 0.12 C here. Okay. So these are again the values. Then you have NACA 6 series. Okay. Here the first digit just represents the series number. So 6 series 6. The second digit represents the location of minimum pressure in 1/10 of C. So here it will be 0.5 C, correct? Yes. Then the subscript gives you the region. So it gives you, so here the value is 1. So it gives you 1/10 above and below the design lift coefficient where there is low drag or favorable conditions where you are preferred to fly the flight. Okay. So the area above the airfoil, above and below the design lift coefficient, where low drag is maintained, the preferable region, not the area, the CL range where low drag is maintained. Okay. So here it would be 0.1, right? The number is 1. Sorry, the number is 1 and in 1/10, so it will be 0.1. So 0.1 above a CL design and 0.1 after CL design, you can fly the aircraft where it gives you the minimum drag conditions. Then the third digit. So the subscript is not considered as a digit. So third digit gives you design lift in 1/10. So here it will be 0.2, right? So it will be 0.2 CL design or CL naught will be 0.2. And 0.1 above and 0.1 below this 0.2 would be the region where there is low drag conditions are maintained. Then fourth and fifth digits, just like the previous 2 cases, give you maximum thickness in 1/10 of C. Here it will be 0.18 C. Okay. These again just give you the values that we had found out. Okay. Now, what is supercritical airfoil? Supercritical airfoil, what it does is that it increases the drag divergence Mach number. Okay. It increases the drag divergence Mach number. Have you heard of this airfoil? So what it does is that a positively cambered airfoil is something like this. Now for a supercritical airfoil, the upper camber, the upper surface is largely flat and the camber is introduced only towards the trailing edge. So it's something like this. Okay. So this is a supercritical airfoil, right? So what it does is that it delays the drag divergence or it increases the drag divergence Mach number. So in our original, in the positively cambered airfoil, maybe at some 0.7, you have a shock wave formed here. Maybe, so this drag divergence, so this, let's say M critical was 0.7, okay? And any flow above 0.7 will be supersonic over the surface of the airfoil and it would give you undesirable flow separation and all of those undesirable traits. Doesn't give you as much lift as it should. So if the same airfoil is replaced with a supercritical airfoil, this M critical is increased. So maybe here M critical is greater than 0.7. Okay. And what happens is that when the shock wave is formed, it forms after. It doesn't form in the beginning of the airfoil. That is why, because of the flat surface, this shock wave is formed aft. So here it says supercritical airfoil also gives you higher drag divergence Mach number. What is this drag divergence Mach number? Critical Mach number, we said, it's the Mach number at which some point on the airfoil experiences Mach 1. What is drag divergence Mach number?
The Mach number at which the drag increases due to wave drag means increases.
Yes, so the Mach number at which the drag increases exponentially. There is a huge rise in the drag after this point. Okay, so we want to delay this also as far as possible because we want to fly for a larger Mach range. So if you delay this drag divergence Mach number, the drag increases exponentially only later. Okay, so supercritical airfoil increases the drag divergence Mach number. The shock wave forms aft when compared to conventional airfoil. Why is this beneficial? Because all of these undesirable traits happen only. Oops. Why does this keep happening? Yeah, all of these undesirable properties only happen after the shock wave, the flow separation and all of that. So if you delay the formation of shock wave, you have delayed flow separation. Okay. Similar to that point, reduces the boundary layer and shock interaction. Again, it's formed later, so it reduces the interaction. Okay. It also gives you a thicker wing when compared to a conventional airfoil. Why does thicker wing mean lighter wing? Why have I written that? Why does thicker wing mean lighter wing? Usually, if you just think about it, if it's a bigger structure, shouldn't it be heavier? Why does thicker wing imply lighter wing? Thicker wings are generally hollow. So when it becomes thicker, it becomes structurally stronger to withstand the loads, aerodynamic loads in flight. Okay, so it requires lesser structural reinforcement. So your struts and longerons, all of them can be reduced. So the weight of all of these structural reinforcements will be reduced and you'll have a lighter wing. Okay, so these are the advantages of supercritical airfoil. Okay, yes, this was the diagram that I was referring to. Yeah, so initially we had seen only this case, right? So when the flow is laminar, when it's approaching the critical Mach number, when it has crossed the critical Mach number, there is a shock wave formed and there's a possible flow separation here. When it goes beyond that, there is a shock wave formed even on the lower surface and there is a definite flow separation towards the trailing edge. As we go on increasing the flight, increasing the Mach number, the flight velocity, this shock wave travels aft, travels towards the trailing edge, and there's a definite flow separation at the trailing edge. Okay. And if it goes beyond this, you have a bow shock at the leading edge and normal shocks at the trailing edge, and the flow is very disturbed, right? It does not give you the desired characteristics at all. Okay, so this was just showing the variation. Okay. Now let's see a few questions that will help you solve the week 3 assignments. So what will be the total fuel weight fraction for X number of mission phases? We have done weight fraction, so I'll give you a minute or two to solve this on your own and then we'll solve it together. Just think about it. What will be the total fuel weight fraction for X number of mission phases? Try doing it. Here, I think there is some ambiguity. So Wx, let's just say it's the weight after, weight after X missions. Okay. So it's like W1 and W2. W0 is the initial weight. W2 was the final weight. So Wx here is the final weight after X missions. Try doing it. B, okay. Okay, let's try doing this. So what is the fuel fraction? So initial weight minus weight after X missions by initial weight. Now what will it be? It will be 1 minus Wx by W0. Yes, so D is the right answer. This is the fuel fraction. Okay. Now let's go to the next question. Very simple. Which of the following is not an application of airfoil? Does it provide lift? Yes. So it does provide lift and lift coefficient, same thing. Does it provide thrust for acceleration? No. What provides thrust? The power plant, right? The engine, the propeller, the jet engine or whatever. Yes, engines. Does the airfoil provide streamlined flow? Yes. What is streamlined flow? Can you tell me? What is streamlined flow? Laminar flow. Yes. Can you, what is laminar flow? Can you define that? In simple terms, I don't need the actual definition, something for us to understand. Where the flow
Movement
lines
is
are.
in-
Yes, yes.
Movement is in the same direction.
Yes, so the flow lines are parallel to each other, right? So there is no turbulence, there is no disturbance, there is no interaction of the flow lines. Yeah, so the airfoil does provide a streamlined flow. So the only thing it doesn't provide is provide thrust for acceleration. That is the right answer. Okay, next. Which of the following is not a type of airfoil? Very simple questions. Vortex, yeah. So symmetric airfoil, we know, cambered, we know, reflexes where it has a slight curvature upward. Now, cambered airfoil exists. Okay, Satvik, this is a positively cambered airfoil. So we just discussed it during the airfoil nomenclature and the terminologies related to airfoil. So cambered airfoil exists, positively cambered airfoil. We have been discussing this throughout this course. Yeah. So what is vortex then? Vortex is not type of airfoil. What is vortex? So have you heard of source where the flow all originates from one point? Or the sink where the flow all goes to one point? Yes, this is source. This is sink. This would have been taught in aerodynamics, but I'm just giving you some information. So these are types of flows, and vortex is one that swirls about a point. Okay, so this is vortex. So these are types of flow. So vortex is a type of flow, not a type of airfoil. Symmetric, cambered, and reflex are types of airfoils. Okay, yeah. So we'll just look at the various types of airfoils that are there. The one that we've been discussing constantly is symmetric airfoil. Is this one, right? Symmetric airfoil where the camber above and below is the same. So the curvature above and below the airfoil is same. Then comes the cambered airfoil. Okay, so there are several types of cambered airfoils, Satvik. There are cambered airfoils, okay? So first one is the low camber, where the upper surface has the slight curvature and the bottom is flat. Then you have deep camber, where you have a greater camber, greater curvature at the upper surface. Then you have deep camber in two types. One is where the bottom is still flat, and the other one where the bottom also has this curvature. It'll just make the wing section thinner. Okay. Then you have reflex airfoil. This is reflex airfoil. Okay, where there's a upward curvature towards the trailing edge. So somebody had defined the reflex airfoil where the chord line cuts through the camber. Okay, so here it goes out of the surface and into the surface. That is the chord line. So it was a definition that I found very different. I liked it. So where the chord line cuts through the camber, right? So that is the definition of reflex airfoil. Then you have this last airfoil, this one. What type of airfoil do you think it is?
Supercritical.
Exactly, supercritical airfoil. So you can see that the upper surface is flattened and the camber only comes towards the trailing edge, and it is thicker. It's something that we have seen. So this is a supercritical airfoil. Okay, this is the one that we discussed that increases the drag divergence Mach number. Okay. Now, a choice of lower thrust to chord ratio will result in. We discussed this when we discussed the properties of airfoil. If you lower the thrust to chord ratio, what will happen? Will you have higher CLmax, higher stall angle, higher critical Mach number, or none of these?
Higher critical Mach number.
Higher critical Mach number, yes. So thickness to chord ratio affects two parameters. One is CL. So that's something like this, right? Where you give a CL max, right? So you can't necessarily say that if you reduce the thickness to chord ratio, it will give you higher or lower. It's just that at that point you get high CL max. It's about 14 to 15%. So we can't really say if you reduce thickness to chord ratio, you'll get a higher CL max. Depends on where you are. The definitive answer is what he said, critical Mach number. So M critical versus thickness to chord ratio, it's something like this. So if you reduce the thickness to chord ratio, you get a higher critical Mach number. This is the right answer. Okay. So this is the actual graph of critical Mach number versus this is thickness to chord ratio. Okay. So this is how it varies. If you reduce thickness to chord ratio, you get a higher critical Mach number. Okay. Then for a cambered airfoil, Cm naught AC of the wing is. We discussed this again. When they say cambered, they mean positively cambered. Okay. Yes, negative, correct. So when will we get positive? Positive Cm naught, when will we get?
Reflex airfoil.
Reflex airfoil, perfect. When will we get zero?
Symmetric.
Symmetric, correct. So this is reflex, this is symmetric, and this is positively cambered. Okay. Let's go to the next question. To trim a flying wing at positive angle of attack, which of the following arrangement is done? We just discussed this reflex airfoil. Okay. So to trim a positive, trim a wing at positive angle of attack, which of the following arrangement is done? Reflex airfoil. Okay. You have a positive Cm naught. So this is a Cm naught greater than 0. Okay. Then what determines the longitudinal stability of an airplane? Relationship of thrust to weight and drag, location of CG with respect to neutral point, location of CG with respect to maneuvering point, none of the above. We just discussed this, right, in the beginning of this lecture? B, correct. So allocation of CG with respect to neutral point. How should it be? So if this is your aircraft and this is your CG, where should the neutral point be for it to be stable? I should in fact ask in another way. So if one So if this is the neutral point, where should the CG be? So you can move the CG. Neutral point is more or less fixed because it's an aerodynamic parameter. And once you fix the wing and tail and other aerodynamic surfaces, neutral point is more or less fixed, right? It is fixed. The CG, however, you can move around. So if the neutral point is given in this line, and this is the fuselage reference line, where should the CG be for it to be longitudinally statically stable? Ahead of neutral point, correct. So CG should be here. Correct. That's when it will give you longitudinal static stability. Okay, let's go to the next question. A propeller-driven aircraft having fuel weight of 650 kg has a fuel weight of 650 kg. Now the aircraft is taxiing on the runway, after which it has a weight fraction of 0.975. Determine the fuel left after taxiing of the aircraft if W naught is 5000 kgs. Try doing it by yourself. Then we'll do it together. Try doing it by yourself. Okay, Satvik says option D. Can you explain how you got there? Can you explain, Satvik? Okay, if you have any doubts, you can ask here directly. But if not, can you try and explain how you did it? Okay, anybody else? Satvik, it is the right answer if you want to explain. Okay, anybody else wants to try or give me a starting point? Where should we start from? We'll do it together. So tell me where to start or how to start. let's try doing it. So they've told you that after taxing, the weight fraction has become 0.975. So initially it was W naught by W naught. So initial weight fraction was W naught by W naught, which is nothing but 1. And after taxing, it has consumed some fuel. And so the weight fraction now has become 0.975. So what happens is that, excuse my poor handwriting. So it's W naught minus weight of fuel consumed, right? By initial weight is 0.975, correct? This is what it says, right? So now let's split it. So you have W naught minus W of fuel consumed is 0.975 into weight is 5,000, correct? So how much is weight of fuel consumed? How much is it? It's 5,000 minus 0.975 into 5,000. How much is this? Okay, Satvik, that's not how you should have done it. We'll just go over this. Okay, so what is 5,000 minus 0.975 into 5,000? How much is that quantity? It's 125, right? So 125 kg is the fuel that was consumed during taxing. Original fuel, how much fuel do we have completely? Weight of fuel is 650 kgs. Now weight of fuel remaining is 650 minus 125. So it will be 525, right? So the answer is 525 kgs. Okay. Okay, let's move on. Is this clear? Okay, let's move on to the next question. So if an airplane has a weight of 180000 Newton at the beginning of the flight and 20% of this is the weight of the fuel, in a flight at a speed of 800 kilometers per hour, the lift to drag ratio is 12 and the thrust specific fuel consumption TSFC of the engine is 0.8. Obtain rough estimates of the range in kilometer and endurance in hour. Okay, so they've asked you for rough estimates. Okay, so take average values and try doing it. Just try doing it. Take a few minutes to do this, and then we'll do it together. Think about it. Think about all the values given in the question, and see how you can find estimates of range and endurance. Okay. So they've asked you rough estimate, so you can take average value. So you can say that the flight speed is average flight speed, that 800 kilometer per hour, and then try finding range and endurance. And then we'll do it together. Just take a few minutes to solve this. Have you been able to do this? Okay, let's try doing it together. So they've asked you about rough estimates of range and endurance. Okay, so range rough estimate would be endurance into the velocity, correct? The rough average velocity. So first we'll find out endurance and then we can easily find out range. How do we find out endurance? Endurance is how much total fuel you have, weight of fuel, by weight of fuel consumed per hour, correct? Weight of fuel consumed per hour. So they've asked you in hours, I've just taken that. So weight of total weight of fuel by weight of fuel consumed per hour. Now let's find out the total weight of fuel. Weight of fuel is what? 20% of the initial weight. So initial weight W naught is 180000 newtons, and weight of fuel would be 20% of that. How much is it? What is the weight of fuel? 36,000 Newton. Correct. So somebody's got range of 3 lakh kilometers. Isn't that a little too much? Endurance is 714 hours, Satvik. That is a huge number. Both range and endurance, your answers are huge. 700 hours with a fuel weight of just 36,000 Newton is huge. Just see where you're making a mistake. And 3 lakh kilometers, I mean, it's huge numbers. They're not the right answers. Okay, so let's continue with this. So weight of the fuel is 36,000 Newton. Now what we need to do, fuel weight consumed per hour. How will we do this? So weight of fuel consumed per hour is thrust required into TSFC, correct? So TSFC is given to you in the question. So TSFC is 0.8. So we need to compute thrust required. How do we compute thrust required? Average thrust required, okay? Thrust required average. What was the formula for steady level flight? What was the formula for thrust required? Thrust required was steady level flight, cruise flight. What was the formula? What was the formula? You have lift equal to weight and thrust equal to drag, right? This was the steady level conditions. From this, what is thrust required? This was, I think, one of the first, third or fourth formula that we had discussed. You divide both of these equations by lift, and then you have thrust is, if you take lift equal to weight, you have W by L by D. Correct? So just do that same thing here, W by L by D. Correct? So W is weight average. Take average weight. WAVG by L by D. L by D is given to you directly, so it's 12. What is the average weight? How do you find this? Can you try solving the question now? Now that everything is given to you, can you try solving it? Satvik, can you try seeing where you made your mistake? Try solving it this way. I'll give you a few more minutes. Just try solving it. Have you been able to do this? Okay, let's just continue. How do you find the average weight? The average weight is initial weight plus final weight by 2. Initial weight we know is 18000 plus how much is the final weight? That is initial minus fuel. So weight final is weight initial minus weight of fuel. Weight of fuel. Oh, sorry. I'll just write another term for this. Final. Okay. So there is no confusion. Initial weight was 180,000. Weight of fuel was 36000. So what is the final weight? You have 14400. Correct. So 144,000 by 2. And what is this quantity? 162,000 newtons, right? So you put this here. So it's 162,000 by L by D is 12. How much is this value? Thrust required, average thrust required. How much is the quantity? Right. So it's 13500 newtons. Okay. Now, how do you find out endurance? You have all the quantities. So what is endurance now? Weight of fuel consumed per hour. Okay, let me just put it here. So how much is this value? So it is thrust required is 13500 into TSFC. TSFC is 0.8, correct? So it's 13500 into 0.8. How much is this quantity? One zero eight zero Newton, correct? Plug it in here. Let's keep this separate. So you have weight of fuel is 36000 and this is 10800. And how much is this value? Endurance. Approximately 3.33, correct. So it's 3.33 hours. And what would the range be then? Endurance into velocity. Just multiply this 3.33 into average velocity, 800. How much will it be? About 2664 kilometers, right? So these are the two values. Is this question clear? Have you understood this? Yes? Okay. There are no questions, then we'll move ahead. Okay. Which placement of wing has least lateral stability? So stability control was a prerequisite to this course. I hope you've done it. So which placement of wing has least lateral stability? High wing, low wing, mid wing, or you cannot say? Which one do you think? B. Why low wing? Can you try to explain? For the answers that you are giving me, can you try to explain? I will try to draw this. So for your, let me do the same thing. So this is your high wing configuration, okay? And if it is rolling, you have something like this. So there is a component of velocity, a normal component of velocity acts in this way, okay? So if you imagine it, you imagine it impinging there, and you have a component of velocity acting in that way, and it produces a restoring moment, correct? So high wing produces a restoring moment. Now, if I have the same thing with a low wing configuration, same roll due to gust, this same normal component of velocity would now act on the low wing. Okay, try to, I'm not sure if I can convey it through this diagram, but its normal component, it impinges on this low wing and it tries to push it further down. So the moment is not restoring, it's disturbing. So it's more destabilizing, correct? So the answer is high wing. High wing is more stable. I think I have a figure. Yes. So the first case is the high wing, second case is mid wing, and third case is low wing. Okay. So when it is subjected to a gust, it rolls towards the right. In this case, if you could see, it rolls towards the right. And the lift produced on the right wing is much higher than the lift produced on the left wing for the case of high wing configuration. So it produces a moment, oops. So it produces a moment in this direction, trying to bring it back to its equilibrium position. For a mid wing, the lift produced is same on both wings, so there is no effective moment. It remains there. Okay. For the low wing configuration, the lift on the left wing is much higher than the lift on the right wing, and it contributes further towards rolling it in the adverse direction. Okay, so it produces a moment in this direction, no restoring moment, it continues rolling. So low wing does not give you lateral stability, high wing gives you more lateral stability. Okay, so low wing, if you introduce something known as a dihedral angle, it contributes towards lateral stability. Otherwise, low wing is not preferred for in the lateral stability aspect. Okay, so I've just summarized the conditions here for different kinds of stability. For the longitudinal case, Cm alpha should be less than 0. This we have discussed extensively, right? What are the structural components that contribute towards Cm alpha less than 0? Horizontal tail. If you introduce a horizontal tail, it makes your provides a restoring moment. Now, in the directional case, what is the condition for stability? C and beta should be greater than 0. And what structural quantities do that for you? Vertical tail, swept wing. Okay, these two quantities, these two structures give you a restoring moment, correct? Then, in the lateral case, for lateral stability, just the one we have seen, is that CL beta should be less than 0. And what structural components give you that? A vertical tail, high wing, or a low wing with dihedral angle. Okay, these components, these structural aspects contribute towards lateral stability. Okay, let's move on. Okay, determine the corrections or otherwise of the following assertion and reason. Okay, first assertion, most of the tails are using symmetric airfoils. True or false? Most of tails use symmetric airfoil. True or false? I think we discussed something similar in the last week. The tails use symmetric airfoil. True or false? True. And why do we prefer symmetric airfoil for tails? Stability. Why, if I have a cambered airfoil, what would it cost for the stability? So the tail is put in place for stability. Why should we choose symmetric? Okay, yeah. So no unbalanced forces at the tail. It's not desirable. So yeah, you're right. Equal force distribution. Yes. Okay. So the first statement, assertion, is true, right? What about reason? The tail control has two primary control surfaces. So they've not said horizontal or vertical tail. So is the statement right? Tail control has two primary control surfaces. So the horizontal tail has the elevator and vertical tail has rudder. So yes, tail control has two primary control surfaces. So this statement is also true. Now look at the options and tell me which is right. Both A and R are true, but is the reason this correct reason for assertion? Yes. So both A and R are true, but R is not the correct reason for A. Correct. Next question. To maintain static stability and trim for a wing canard aircraft, which of the following conditions should be met? Read the question options carefully. What is a canard? What is a canard?
A horizontal tail is before the wings.
Correct. So an aerodynamic surface ahead of the wings. Correct. Okay. So for such an configuration for a wing canard aircraft, what should be the condition to maintain static stability? Read the options carefully and tell me the correct answer. Let's just look at the different cases. So if it's just a wing, what do we require? We require the CG to be ahead of AC, correct? For static stability, longitudinal static stability, we require the CG to be ahead of AC. So when I had done a course on flight stability control, when the professor had asked us to perform this basic experiment of taking any rectangular cross section as a wing. So I took a piece of thermocol and tried flying it. So he asked us to try flying it, and it would obviously flip over, it would be unstable. And then the next thing was to add weight. So initially I had taken a thermocol sheet. So the aerodynamic center is somewhere at the quarter chord point. So this is the aerodynamic center, and CG is here. Without adding any weight, initial CG is here. So when I fly this, it would not fly stable. It would not be a smooth motion. It would keep flipping over. And so like we require the CG to be ahead of AC, right? So what we did was we added weight at the nose. So we progressively added weight at the nose such that the CG gradually moved ahead of the AC. And when we added sufficient weight to ensure that the CG moved ahead of the AC, and then we flew this same thermocol sheet, it flew smoothly, right? It just glided to the ground. It did not flip over in an unstable manner like the previous cases. Similarly, he had asked us to do a wingtail configuration and perform the similar experiment. So that would be a neutral point. In this case, the CG has to be ahead of AC. In the wingtail configuration, CG has to be ahead of the neutral point. Okay. So in this simple wing configuration, your CG is ahead of AC. Now, if you have a wing tail configuration, the overall aerodynamic center, so aerodynamic center of the wing is here in blue, of the tail is here, okay? Then the overall, if it was just wing, the neutral point and AC are the same. Now you've added an aerodynamic surface behind, that is a tail. So the aerodynamic center is pulled backward. Okay, aerodynamic center of the aircraft, neutral point, is pulled backward. And the stability condition is modified such that the CG should be ahead of neutral point. Now, when you add a canard, it is a aerodynamic surface that is added ahead of the wing. So your neutral point is pulled forward. Okay, so the CG now has to be moved further forward. So for the stability of the wing canard configuration, CG has to be between canard AC and wing AC. So what were the options? Location of center of gravity must be aft from wing, between wing and canard, ahead from canard. Should be between wing and canard, right? Is this clear? Is this clear? Okay. Next, if the tail volume ratio increases from 0.45 to 0.55, how will it affect the stall speed of the aircraft? So what was tail volume ratio, VH? Do you remember what was the formula? VH is equal to, this is from your stability control course. What is the formula?
S tail, L tail by S C.
C, correct. Where S tail is the area of the tail, S is the area of the wing, C is the main chord, and LT is the moment arm. Okay, between the aerodynamic center of the tail and the CG. Okay, so now tell me if this change in VH would affect Vstall. Change in volume ratio from 0.45 to 0.55. How will it affect the Vstall? What was the Vstall formula that we've been using throughout? Is under root 2W by S by rho CL max. So if I increase volume ratio from tail volume ratio from 0.45 to 0.55, how will it affect the stall velocity? Does VH appear anywhere in the Vstall equation? No. So change in VH, change in tail volume ratio does not affect the stalling velocity. So it remains same. Okay. So these are the formulae. So Vstall formula we know. VH only appears in the tail contribution towards pitching moment. So this is the tail contribution towards Cm naught. And this is the tail contribution towards Cm alpha. Okay, so this is where VH appears. So it only affects the stability and the trim angles, does not affect the stalling velocity. Okay, okay. Next question. The pitching moment coefficient about the leading edge of an airfoil is given by Cm equals minus 0.149 plus 0.0298 alpha, where alpha is the angle of attack of airfoil in degrees. What is the trim angle of attack of airfoil in degree? How do you find this? How do you find this? How will you do this? Just try doing this by yourself. It's a very simple question. Could you do this? What is trim? What is trim? Making CM not zero, where the summation of forces and moments are zero. Correct. So if I make CM not zero, what is the angle of attack? So CM equal to zero, CM equal to zero. So it will be minus 0.149 plus 0.0298 alpha equal to zero, alpha trim. So what is alpha trim? 0.149 by 0.0298. What is this value? 5 degrees. Correct. So that is the trim angle of attack. Okay. Okay. So let's go to the next question. When the angle of attack decreases, the moment of center of pressure will be. When the angle of attack decreases, the moment of center of pressure will be. Center of pressure we just defined as the point about which the aerodynamic forces act, lift and drag act. And it keeps moving with angle of attack, which is why it was inconvenient for us to perform analysis. And we came up with aerodynamic center. So now the question asks you, when the angle of attack decreases, how will the center of pressure move? Towards trailing edge, independent of angle of attack, towards leading edge, all of these. So it is not independent of angle of attack, right? That is aerodynamic center. So it is not this. So does it move towards trailing edge or leading edge? Think about it. I will give you a hint and you try finding it out, finding out the answer to this question. We'll discuss it next week. So try drawing your pressure profiles, okay? And see where the net pressure or net forces act. Just draw the pressure profile and try to find the center of pressure, right? And then try increasing angle of, just draw the pressure profiles for 2 or 3 different angles of attack, like when it increases, when it reduces, and then you'll be able to answer this question. We'll discuss this in detail in the next week. All the very best for your week 3 assignments. Is there any doubt? Does anybody have any doubt? So Satvik had some doubts, but they were in general, he had some doubts. Do put up your questions on the forum so we can answer them. So, yeah. Does anybody else have any other questions? If not, we'll end the session here. We'll get back to this question next week. Do check out the pressure profiles of different airfoils at different angles of attack, and then you may be able to get the answer. If not, we'll solve it next class. Okay, if there are no doubts, then I think we'll end the session here. Thank you very much and all the best for your week 3 assignments. Satvik, please put up your questions on the forum. One of us will get back to you. Thank you. We'll meet again next week, next Tuesday. Thank you.